Every beat of your heart and every breath you take serves one ultimate purpose: keeping your cells fueled. Deep inside those cells, that fuel takes the form of ATP, the microscopic energy currency that powers enzymatic activity, protein synthesis, and every ionic gradient in the human body. To maintain a steady supply of ATP, your body relies on a meticulously balanced delivery system. It depends on three parameters working in harmony: the heart acting as the pump, the blood mass representing the content, and the vascular system as container. We can see how this delivery system functions in this visual equation. Tissue perfusion, the total amount of oxygen reaching your cells, is the product of arterial oxygen content and your cardiac output. The purpose of the cardiorespiratory system is to deliver oxygen and glucose to the cell to power aerobic metabolism. As long as this flow is maintained, the cell constantly produces ATP and eliminates CO2 and water. Human health relies entirely on this delicate equilibrium. The exact amount of oxygen demanded by your cellular metabolism must constantly be met by the supply delivered through your bloodstream. When this equilibrium fails, the body enters a state of acute systemic circulatory collapse. In medicine, this is defined as shock. Look at this microscopic view of a healthy cell losing its oxygen supply. When the supply chain breaks, energy production halts, the cell's internal machinery freezes, and the body begins accumulating a mounting systemic energy debt. Once aerobic metabolism stops and that energy debt begins, the condition is not spontaneously reversible. In the absence of immediate treatment to restore the oxygen supply chain, this energy debt initiates a fatal, irreversible countdown. There are two distinct ways this delivery chain can fail. The first is quantitative shock, where the physical volume of oxygen being delivered to the tissues drops below the level required for survival. This occurs in hypovolemic shock, through the loss of blood or plasma, and in cardiogenic shock, where the heart muscle itself fails to pump effectively due to infarction, rhythm disorders, or valvular damage. When oxygen delivery drops, the body initiates a sympathetic reaction. It floods the system with catecholamines, specifically adrenaline and noradrenaline. During the adrenergic response, massive vasoconstriction in the skin, kidneys, and GI tract redirects oxygen-rich blood toward the brain and heart. Deprived tissues shift to anaerobic ATP synthesis, producing lactate. This lactic acidosis causes the closed precapillary sphincters to fail. The localized acidosis paralyzes the sphincters, causing them to spring open. This leads to massive, uncontrolled vasodilation and a sudden, catastrophic plunge in tissue perfusion pressure. In quantitative shock, the body's own desperate attempt to hoard oxygen ultimately triggers the final, irreversible circulatory collapse. The second mechanism is distributive shock. In this state, oxygen delivery might appear adequate, but the local distribution of blood flow is profoundly dysregulated. We see this failure in septic shock, caused by microbial invasion, and in anaphylactic shock, triggered by severe allergic reactions. To understand this, look at the vascular endothelium. In septic shock, cytokines tear gaps in this lining, leaking plasma and triggering intravascular coagulation that blocks flow. In anaphylaxis, histamine drastically expands the capillary, causing blood to pool sluggishly in overexpanded vessels. Whether leaking fluid through damaged walls or pooling in dilated vessels, distributive shock starves cells of oxygen by destroying the container meant to deliver it. Regardless of whether the initial trigger was quantitative or distributive, the shared endpoint is profound, systemic cellular hypoxia. When hypoxia is prolonged, the brain slips into coma or ischemic stroke, while the heart suffers coronary hypoperfusion and metabolic impairment, leading to myocardial infarction. The filtration systems fail next. The kidneys stop producing urine, a state called oliguria, while the liver undergoes hepatocellular necrosis or hypoxic hepatitis as its cells die. Fluid fills the lungs in lesional pulmonary edema. The gastrointestinal tract begins bleeding from acute ulcers, and the coagulation system fails entirely. This cascade of multi-organ failure is the macro-level consequence of billions of individual cells running out of ATP. Shock is an acute circulatory failure where oxygen supply no longer meets cellular demand, an energy debt that the body cannot resolve on its own. survival is entirely dependent on the rapidity of treatment. A clinician must quickly identify the correct etiology and restore the oxygen supply chain. The margin between cellular survival and death is determined by time. Medical intervention must restore the equilibrium of oxygen supply and demand before the body's energy debt becomes permanent.